So you open up a map app on your phone, right? You're trying to navigate a new city, or maybe you just ordered a ride, and you watch that tiny little car icon pull up literally exactly to where you're standing. We do this, multiple times a day? And we don't even give it a second thought. But how in the world does your phone actually know your exact coordinates, down to the meter, at any given moment?
Well, the secret isn't in the phone itself. You actually have to look up, way, way up. The answer is an invisible, highly complex infrastructure orbiting roughly 20,000 kilometers right above your head. It's up there right now, silently powering the modern conveniences we rely on every single day. Okay, let's dive right into this explainer. Today, we're exploring a really fascinating region of space. It's often called the Goldilocks orbit, but technically it's known as medium Earth orbit. We're going to break down what makes this specific band of space so absolutely crucial, how on Earth satellites survive up there, and why our entire modern civilization would, quite literally, grind to a halt without it. Section 1. The middle ground of space. Let's pinpoint exactly where this orbital real estate actually is. So medium Earth orbit, or MEO for short, is this massive, sprawling middle zone. It sits perfectly sandwiched right between low Earth orbit, which is where things like the International Space Station hang out, and geostationary Earth orbit, which is way, way further out. We're talking about a region of space that spans from roughly 2,000 kilometers all the way up to an astonishing 35,786 kilometers above the Earth's surface. I mean, that is a massive chunk of territory. You can really think of MEO as the ultimate cosmic compromise. See, if you put a satellite down in low Earth orbit, it has a very low communication delay, which is awesome, but it can only see a tiny little sliver of the Earth at any one time. But if you move it up to MEO, you strike the perfect balance. You get a much larger global coverage area, and you only have to deal with a moderate delay in communication. It's literally the sweet spot. And the numbers here reveal a huge operational advantage. Because MEO goes all the way up to almost 36,000 kilometers, it takes a satellite anywhere from 2 to 24 hours to circle the Earth. Compare that to just 90 to 120 minutes down in LEO. Crucially, up in MEO, atmospheric drag is practically non-existent. Plus, because each satellite can see so much more of the globe from that high up, you need a far more moderate number of them to create a global network. You just don't need those massive, sprawling thousands of satellites constellations like you do in lower orbits. Moving on to Section 2, Mechanics of Medium Orbit. How do objects actually move when they're floating around in this massive middle zone? Well, if you were somehow floating up there, these satellites would go absolutely screaming past you at incredible speeds, somewhere between 3 to 7 kilometers per second, depending on their exact altitude. Just think about that for a second. Up to 7 kilometers in a single second. Yet, kind of ironically, in the grand scheme of orbital mechanics, this is actually considered a slower, almost leisurely pace compared to the super-fast satellites zipping around down in low Earth orbit. The physics dictating this whole environment really just come down to one fundamental equation. Don't worry, we won't get bogged down in the math, but basically, velocity equals the square root of the gravitational constant times Earth's mass, divided by the radius. All you really need to take away from this is the rule it creates. As the distance from Earth increases, the satellite's speed naturally decreases, and the time it takes to complete an orbit gets longer. That is exactly why MEO satellites take up to a full day just to go around the planet once. And because of these physics, parking a satellite in MEO brings some massive benefits. A larger coverage area means ground stations don't have to constantly hand off signals to each other, so the network is way simpler to run. Longer satellite visibility means your communication is a lot more continuous, and navigation is way more accurate. Plus, with negligible atmospheric drag, the orbit hardly ever decays. That means these satellites need significantly less fuel and can stay operational for a much, much longer time. All right, Section 3, Pros, Cons, and Radiation. Because it's time we look at the darker side of this orbital sweet spot. MEO comes with a really intense, dramatic trade-off. On one hand, you have this peaceful void with basically no atmospheric drag tearing at the spacecraft. But on the other hand, MEO sits directly in the crosshairs of the Van Allen radiation belts. This is a highly dangerous, intensely charged environment that's captured and held right in place by Earth's magnetic field. These radiation belts are absolutely a spacecraft's worst nightmare. Those highly energetic charged particles, they can inflict immediate serious damage on sensitive electronic components. Over time, they literally degrade the solar panels, slowly starving the satellite of its power. And they constantly mess with onboard computers, skyrocketing the risk of what engineers call single-event upsets. This is essentially a rogue wave of radiation flipping a 1 to a 0 in a computer system. It causes sudden, unpredictable, and sometimes completely fatal glitches. And beyond the radiation, there are some real economic and physical limits to consider too. Actually reaching this orbit requires a lot more launch energy and much larger rockets, which, as you can guess, significantly drives up the cost of the mission. Also, while the signal delay is definitely better than geostationary orbit, it's still higher than low Earth orbit. So for those ultra-fast real-time communications, it's just slightly less efficient. Section 4. Surviving the middle orbit. Knowing about all these intense hazards, how do we actually survive up there? How do we build machines capable of living in that environment? Engineers basically have to tackle 4 critical challenges. First up, to beat the radiation, spacecraft are armored with heavy shielding and specialized radiation-hardened electronics. Second, they need incredibly reliable power systems. Think super durable solar panels and heavy-duty rechargeable batteries to endure these long missions. Third is thermal control. Satellites up there bounce wildly between blistering intense sunlight and freezing cold eclipses, so they're wrapped in multi-layer insulation and use special radiators and heat pipes to survive. Finally, orbit maintenance. Even without the atmospheric drag, engineers still have to constantly fight the pull of lunar gravity and the literal physical pressure of sunlight pushing against the spacecraft. Section 5, Real-World MEO Applications. Let's bring this all back down to Earth and look at who is actually using this specific space. MEO is essentially a who's who of major global players, which really shows you just how critical this region is. The United States operates GPS here. The European Union has Galileo, China runs Beidou, and Russia manages GLONASS. All of these are major global navigation systems just coexisting right there in the middle orbit. You've also got private constellations like SES's O3b mPOWER network, which uses MEO's lower latency to beam high-speed broadband internet straight down to us on Earth. So what are all these constellations actually doing for you and me on a daily basis? Well, they provide the position and navigation stuff we talked about at the very beginning. But even more vitally, they provide precise timing and synchronization. This is huge. Global financial networks, cellular towers, our power grids, they all rely entirely on the ultra-precise atomic clocks ticking away on these MEO satellites just to stay perfectly synced. They also handle broadband data and even host scientific instruments to monitor space weather. The whole point is summarized perfectly by this quote from our source materials. As global dependence on navigation and timing services continues to grow, MEO will remain one of the most important orbital regions for future space missions. Our modern, fast-paced, interconnected civilization is quite literally tethered to this specific band of space. Which leaves us with a pretty critical question to ponder. We've seen how perfectly balanced this Goldilocks orbit is, but we've also seen how completely punishing that radiation environment can be. With our entire modern world relying on this invisible, radiation-filled sweet spot for navigation, banking, and communications, what happens if MEO gets too crowded? Or what if a major space weather event damages this vital infrastructure? It is a fragile equilibrium floating 20,000 kilometers above us, and I have a feeling you're never going to look at your map app quite the same way again.